So we want to somehow derive a formula for estimating the error. What would be the error for my function? So as we know, the integration I that we calculate is basically the integration from an x of I minus 1 to x of I, and we know that x of I minus x of I minus 1 is the delta x or the h. It's either this or that. Some books use it h, or some books use it as delta x. So I have here my function that I am interested to find the integration, and this will be the capital f of x of I minus f of x of I minus 1, which is the limit of my integration. Now, what is this capital F? What is the relation between small f and the capital F? It's nothing but the capital F of x of I is the derivative of this is equal to f of x of I. How this is possible? If I take the integration of both sides, this will be this, and if I take an integration of a derivative, I will cancel, so I will get this. Okay, so basically, this is the definition of my integration. Okay, now we know that f of my x of I minus 1 is nothing but my f of x of I minus h. Okay, so this is the function defined at x of I minus h, or x of I minus minus delta. And from the Taylor expansion, we derived this before. If I have a function defined at certain point, then I can find the function defined at plus delta x or minus delta x. So this function is equal to, or this, the same thing, is equal to the function at the defined location minus h times the derivative of the function, all defined at x of I, plus h squared divided by 2 factorial f of double x of I minus h cubed over 3 factorial, the third derivative of x of I, plus, and so on and so forth. And you see here, this is a minus sign here, a minus sign there. Why is that? Because we have minus h. If this is f of x of I plus h, the only difference will be this will be plus and this will be plus. And we derived this before. Now, if I take this to the other side, what I will have I will take this quantity to this side, and I will move everything else to the other side. So I will have f of x of I minus f of x of I minus 1 equal to, now moving this to the other side, is equal to h f prime of x of I minus h squared over 2 factorial f double prime of x of I plus h cubed over 3 factorial f double triple minus so on and so forth. Okay, so far I didn't do anything, defined the integration. Okay, then I said, okay, this term we found it from the Taylor expansion from a previous lecture. I recommend you to go and check this. And then I'm just rearranging the terms. Now, what is this actually? What is f of x of I minus f of x of I minus 1? This is the integration, basically. So the integration itself is equal to all of this, is equal to h f prime of x of I minus h squared over 2 factorial f double prime of x of I plus h cubed over 3 factorial f triple of x of I minus so on and so forth. So now I defined the integration in terms of the derivative of the original function. Now it would be more convenient to me to define the integration in terms of the original function, not its derivative. And we know the relation between the two. We know the relation between the two, that we know that f prime of x of I is equal to f of x of I. We know that. And this is how it was defined before. Okay, so now I will just substitute f prime with the original function. Okay, now when you take the integration of this is what we'll have. Okay, we'll cancel the integration. So this is the relation between the function and its derivative. Okay, so this becomes now h f of x of I minus h squared over 2 factorial f of x of I plus h cubed over 3 factorial f second derivative of x of I, and so on and so forth. Okay, so now I have, with the help of Taylor expansion, have a relation between the integration and this is f prime, the function, its derivative, second derivative, etc., and h, where h is the increment that I select. Okay, I will answer all your questions, or let me just see if there, I think there's just one question. Let me just try to answer it now. It says middle term should be f prime. Yes, yeah, thank you very much. It's f prime. Okay, okay. So now, so good. It's very simple, very easy to understand. No problem. Let's move on. Okay. Now, also from the previous set of notes, we defined from the derivative that f prime is equal to the definition of the derivative plus the error, which is in the second order of h over 2 with the second derivative. This is also has been previously derived. So what I will do, I will substitute this formula with this one, and I will do some sort of manipulation. Okay. Now, so if I substitute this equation in the previous one, I will get this. So your integration now will equal to this formula. I'm just only substituting the f prime of x of I with its value in the integration formula, collecting terms. So I will get this formula. Now, what is this? Okay, this is basically a of I. This is the numerical integration. Okay, if you recall that we have our integration that we defined when we have n equal for one segment only, the integration for that for one segment only using the trapezoidal rule is the following. We know that the integration is equal to b minus a f of a plus f of b divided by 2. Now, for one segment, for only one segment, b minus a will be your h. We will have h over 2 times f of x of I is your f of b, and f of a is f of x of I. So this is the numerical integration. So if this is the numerical integration, so this is the actual integration, and this is the numerical integration. So the difference between the two will be what? Will be the error. So if you take the difference between this and this, we will get the rest of the terms, which are the error. So this is the error. Now, if we ignore the higher order terms, you can state that the error magnitude is equal to h cubed divided by 12 f double prime of x of I. Okay, so this is your error. H cubed over 12 times f double prime x of I. This is by ignoring the rest. But this is true for only one segment. Okay, let's move on. Now, what is this f prime? This is a function defined in the interval from A to B. Okay, so if this has a maximum point, or if this value is less than certain value of m in the whole interval, then I can say that the error is less than or equal to h cube over 12, and I will substitute the f double prime with an m value, but now this becomes less than or equal. Okay, and I will see how I can find this. We will see some examples, and we'll see what. So now I know that my error is less than or equal to this value, which is a function of two things: h cube and m. M is the maximum, the double derivative of x of I, absolute value, is less than or equal to this m value. Now, this is only for one interval. This is only, if this is my function, this is only for one interval, which I define as x of I minus 1 and x of I, which is h. Now, if I want to expand that to the whole thing, I need to multiply by n. So if I multiply everything by n, okay, then what is n? N, we know it, is equal to b minus a divided by h. So I will substitute with this b minus a over h. So this h will cancel with h cubed. So I will have this formula, which is a very interesting formula that will give me the relationship between the error, the maximum error that I can get is less than or equal to b minus a, which is the limit, the bigger. Now this is valid for any number of n, not just for n equal to 1. This is equal, or this is true for any number of segments. Okay, h is the width of that segment, and m is greater than or equal the f double prime. Here there's something very, very interesting. If we just go back, we said that the error, okay, is equal to h cube divided by 12 f double prime of x. Now, if I have a linear function, meaning what? My f of x is equal to a0 plus a1 of x. So what will be the f prime of this? This will be a1. What is the f double prime of this? This becomes 0. And this is why when we have a linear function, that the error will be 0. This is another way of looking to the same thing. This is why when we had in the previous example, when we have a straight line, mean the relation is a linear relationship, your error was 0. It doesn't really matter what is the value of h. You can have any h, and still you will have an error. So you can have n equal to 1, n equal to 2, 4, etc. And still you will have an error. And now we understand it in a better way, that the error is basically proportional to f double prime. And this is why in the trapezoidal method, the error will be equal to be 0 if we have a linear function. Okay, so let's have this. And this will also give us some important insight about it will give me an important insight about the practical use of the previous formula. So here is this question. And by the way, in the practice problems, you have some of those questions. Determine the number of sub-intervals n. So I have here a curve, and I want to divide this curve into an n number of segments. So that I don't know yet. Okay, now the selection of n will be based on the error. The goal here is to find certain error. So here I want to so that we will get the error less than 10 to minus 4. So that is the objective, and this is the function that I am really interested in. So with this, now we will try to understand. Now we said that, okay, that the error will be equal to less than or equal to b minus a times h squared divided by 12 times m. Okay, so this is the error, which is I know, okay, and this error, as we know, or I can write this in a different way. If I want to find n, this is the same formula. This becomes equal to n h cube divided by 12, and we know that this and this formula are exactly the same thing. Now n is what I want to find, so this is unknown for me. The error is given to me 10 to minus 4. H squared, this is related to my n. Okay. Now once we know h, I can use this formula to find h, and I know the relationship between h and n. Okay. We know that h is equal to b minus a over n. Okay. So I can this is in this equation I will have two unknowns, n and h cube. It's better to start with this formula. Why? Because b and a is given to us. This is your a and this is your b. Okay, so this formula now will have two unknowns. It's better to delay it now, not to use it, and instead using this one. And from this you can tell that n is b minus a divided by h. Okay, now what is left is m. And we said that m is the maximum value of the second derivative. Okay, now as we know, this is the function f of x is equal to 1 over x plus 4. So what is f prime of x? This is equal to minus 1 over x plus 4 squared. What is f double prime of x? This is equal to 2 over x plus 4 cube. Okay. Now the question is, what is the maximum value of this? But that's not for any number, but for the interval a of b, which is 0 and 2. Now when you substitute, it's very clear that the maximum value will happen at x equal to 0. Very clear. Because as we increase x, this number is going down and down. So 0 is the maximum value of f double prime. So f double prime at 0 will give me m, which is equal to 1 over 32. So this is the maximum value. Now we know m, we know the error, we have everything here now. So you can say that 10 to minus 4 will be less than or equal b minus a, which is 2 minus 0, times your h squared, my unknown, divided by 12 times 1 over 32. So if you solve for this inequality, h, which is equal to now b minus a over n, which is 2 divided by n, has to be less than or equal to 0.13856, and from this your n has to be greater than or equal to 15. Of course, n cannot be a real number, it has to be an integer. Okay, so if you get n equal to 14.6, then it has to be 15, and so on and so forth. So your n, if you have an n greater than or equal to 15, you would be able to achieve this error. So you can see here, I can select the number of segments based on this important criteria, which is the error. Okay. Now let me give you another example to demonstrate this. That you have an f of x is equal to 0.2 plus 25 of x plus 3x squared. Okay, and I want to use for n equal to 1, just n equal to 1. I want to estimate the error and I want to calculate the error. Both estimate the error and calculate the error. Okay, so I want to find the exact integration. Okay, so the exact, and this will be defined between 0, the a and b, from 0 to 2. So I will find first the integration I is equal to from 0 to 2, 0.2 plus 25x plus 3x squared. Without going into details, this is equal to 58.4. So this is my actual integration. Let me find the approximate integration a, which is equal to b minus a divided by 2 f of a plus f of b. Now we substitute. So f of a is, this is your a and this is your b. So f of a means f of 0, you substitute here, 0.2 plus 0 plus 0, so this becomes 0.2. F of b is 2, so you come here and substitute, you will find this is equal to 62.2. This is 2, so this will cancel, so this gives you 62.4. So what will be the error now? The actual error, the exact error, will equal to 62.4 minus 58.4, which is equal to 4. Now, let's find the estimate of the error. Okay, the estimate of the error, as we know it, error is equal to approximately b minus a each square divided by 12 times 6. Okay, and what is your h? H is equal to b minus a divided by n. Okay, and I will use one segment, so this h is equal to 2. So if you calculate this, you will find this is also equal to 4. Now the question is, if you recall, we ignored higher order terms. Okay, so how come? So this is an approximation. Now becomes exact. Why the error using the exact calculation and the error using the approximate calculations is okay? So let me give you let me give you the whole formula. If there's something that is missing, okay. You ask where is 6? Okay, thank you very much. Let's go back to the formula, original formula. Let me sorry, I went a bit fast here. So the formula is equal to as we mentioned before, it is equal to b minus a each square divided by 12 times m. And what is m? M is the maximum value of f double prime of x. Take the double prime of f of x, you will get this is equal to 6. It's a constant value, so this becomes equal to 6. Okay, so this is why we have 6 here. Okay, so this is the second derivative of x. Okay, hopefully this is clear now. Okay, now the question is, we said that a of t is less than or equal. Now it becomes exact. So this is supposed to be less than or equal. Why it is exact? The reason for that because the higher order terms has a term multiplied by higher order derivatives, third derivative, fourth derivative, and we know that the third derivative, fourth, fifth derivative of this term will be 0, always 0. So if I have a second order function, I can exactly find the error. Okay. Now, if you go n equal to 2, do the same thing, you will find the exact error as well, and so on and so forth. So I thought this is an interesting point to link how to find the error and to understand the meaning of this m and f double prime. Okay. Now I will just touch base of the second method, which is more used than the trapezoidal. Is easier, but this is the basic. Now let's remember, I have a function here and it has a limit. I want to find the integration. In the trapezoidal, we assume that the function, that link between a and b, is a linear function. This is what we assume, and then we will find the area of the trapezoidal. So what if I assume that the relation between A and B is not linear but non-linear function. So we have something like is more non-linear function, second order or a third order. Now the Simpson one-third rule, assuming that the function between A and B will become a second order polynomial, not a linear function. So here, uh, as I said, the trapezoidal is based that we have a first order polynomial or a linear function. Now the Simpson's one-third rule, this is using it's just an extension to the trapezoidal rule, and here we assume that we have a second order polynomial. Now to find a second order polynomial, we need to have 3 points. If you recall, go back to the way we found the polynomials. Okay, so if we want to have first order, then I have to have 2 points. If I want to have a second order polynomial, I have to have 3. So always the number of points is higher by 1 degree than the degree of the polynomial. Okay, so here I have to have 3 points so that I will be able to find a polynomial to approximate this. Before, for the trapezoid, I need only to have 2 points, this point and that point. Now I will define another point at the middle, a plus b over 2, and hence the x, this is the x value of this, and this is the y value, which is just finding the function at this. So this is the function at a plus b divided by 2. Okay. Now the derivation here, you don't need to know it. I will go a bit fast, and our interest is in the final formula, but we will derive this. And by the way, you can do that yourself, because we know that from the previous studying about interpolation and using the direct method or the Newton method to find the polynomial degree that we want. We'll do exactly the same thing here. Okay, so now my integration between a and b, now it is this is to refer to the degree of the polynomial. Before we have first order, so we have this is as 1, now this is 2. Now this is my function here that I want to find. Now this function, I need to find a0, a1, and a2. Now we have 3 unknowns. As we know from the direct method, to be able to find those unknowns or constants, you have to have 3 equations. Okay. Now as we know, we have these 3 values. We know the function at a and f of a. We know the function at f of a plus b over 2, and we know the function at b. So this is our first, second, and third point. So we know all of them. So I will have 3 equations. Now instead of having f of 2 of x, I will have f of 2 of a equal f of 2 of a plus b over 2 equal, and f of 2 of b equal. So I will substitute the x with a plus b over 2, and b. Then I will have 3 equations, and the unknowns now a0, a1, and a2. Everything else is known to me. Then I will solve these equations. Okay, so this is the 3 points: a, f of a plus b over 2, and f of a plus b over 2, and b and f of b. Now we have the 3 points, so I will have the f of a plus b over 2, and f of b. Okay, so this are the 3 equations: 1, 2, 3, and you can see that solving this symbolically will not be trivial. Okay, so we'll go through a lot of mathematical manipulation, because these are not just numbers; these are symbolic. So I wanna come up with a general formula. So as I said, we don't need to understand or to know. We need to understand, of course, but we don't need to know how to derive this. So now when we solve, we will get up these 3 formulas. This is for a0, a1, and a2, and you can see the formula is a little bit complicated. Now I will use these in the function f of t of x, which is equal to a0 plus a1 of x plus a2 of x squared. Now I will take up this, and I will substitute them to find the integration now of this. And here is the if I do take the integration of this. Okay, and then I will end up having this interesting simpler formula. This is the formula, which is, you can see here, it has some similarity with the previous uh, formula that we have, which was b minus a over 2 f of a plus f of b. Now we have something here extra because of the a plus b over 2. Now remember, this is for if I use the, assuming that the whole area is between a and b. We have only one formula. But remember now, I have to have 3 points. Okay, so now I will have 2 segments, although I'm having n equal to 1 here, but actually we have to have 2 segments. Why? Because I need to have 3 points. Okay, in linear relationship, if you have, this is the function, I need only a and b only. So we have only one integration. Now here we will have like two segments. So for n equal to 1, we have 2 segments. N equal to 2 will have 4 segments, and so on and so forth. Okay, so this is the formula that we will have, and this is your h, b minus a over 2. Why over 2? Because we have 2 segments here. So your h is equal to, we have two segments here, and you can write down the formula in terms of h. Okay, but remember, this is now, I'm assuming that I defined only one formula from a to b. I'd like to stop